Science depends on experimentation, which requires measurements. A measurement is a quantity that has both a number and a unit. This scale shows a measurement of a person's mass that is 135.2. Above the 0.2, it shows the measurements is in pounds. The unit of measurement is important because a 5'6" person with a mass of 135 pounds would not be considered overweight. But if the unit was 135 kilograms, they would be considered overweight. In chemistry, two common measurements that are made are mass and volume. Mass is the quantity of matter in an object. Volume is the amount of space an object occupies. In science, we use the SI units for measurement, or the International System of Units. We call it SI and not IS. This is because it comes from the French term Système International des Units. SI units comprise a system of units of measurement devised around 7 base units and a metric system. It was established in 1960. This table shows 7 SI base units: kilogram for mass, meter for length, Kelvin for temperature, second for time, mole for pure substance amount, ampere for electric current, and candela for light brightness. In chemistry, a kilogram is a large quantity, and it makes more sense to use grams than it does kilograms. 1 kilogram equals 1,000 grams. Volume is considered a derived unit and not a base unit. This is because volume comes from an equation of volume equals length times width times height. So length is a SI base unit, but volume is a derived unit. The SI unit for volume is 1 meter cubed. My program doesn't allow me to write cubed as a superscript, so I've used the caret symbol like on your calculator to show that it's raised to the 3rd power. A 1 meter cubed is not convenient for use in chemistry either. It's too large of a quantity. So chemists use liters or milliliters or cubic centimeters. So 1 liter equals a 10 centimeter by 10 centimeter by 10 centimeter cube, or 1,000 centimeters cubed. 1,000 milliliters also equals 1 liter. So therefore, 1 centimeter cubed equals 1 milliliter and can be used interchangeably. On many units of density, you'll see the units recorded as grams per centimeter cubed or grams per milliliter. Usually for solid objects, we use grams per centimeter cubed, like gold or sodium. But if we're talking about something that's a liquid, like a solution, we would use grams per milliliter for density. Another measurement in chemistry is temperature. We commonly take temperature readings for things. The SI unit for temperature is Kelvin. Kelvin is based on the absolute zero of objects, meaning they have no kinetic energy and they're not moving at all, being 0 Kelvin. But we need to, sometimes we can't measure. Thermometers don't measure in Kelvin. They usually measure in Celsius. So 0 degrees, or I shouldn't say 0 degrees, 0 Kelvin, we don't use degrees for Kelvin. 0 Kelvin equals negative 273 degrees Celsius. We do use degrees when we say Celsius, and if it's Celsius, it should have a little degree or a little O circle written as a superscript right after the 3 and before the C, but this program doesn't let me write it. So let me say that again. 0 Kelvin equals negative 273 Celsius. So that's also absolute zero, where matter has no kinetic energy. Now, 0 degrees Celsius equals 273 Kelvin. Alright? So 0 Celsius is the freezing point of water. That is 273 Kelvin. 293 Kelvin equals 20 degrees Celsius. That's room temperature, about 70 degrees Fahrenheit. If we want to be able to convert Kelvin and Celsius, it's really simple. If you want Kelvin, you take your Celsius degree temperature and add 273 to it. If you want Celsius, take your Kelvin and subtract 273. In chemistry, we want experimental measurements to be reliable. We want them to be correct, or close to the ideal or true value, and reproducible, meaning we can get similar measurements again and again. Accuracy is how close a measurement comes to the actual true value of whatever is measured. The top graphic shows arrows that are close to the bullseye and have a high accuracy. Precision is a measure of how close a series of measurements are to one another. The bottom graphic shows arrows that are close to each other, which means they're reproducible, but not close to the bullseye or accurate. In other words, you want your data in chemistry to be both accurate and precise. Say you're boiling water, and you have a thermometer in the water, and you notice the water's boiling. You read the temperature on the thermometer, and it says 99.1 degrees Celsius. You know water boils at 100, so your thermometer there is not perfect. It's pretty accurate, but it's not perfect. So you can figure out what's the percent error of your thermometer. If you have ever looked at a large thermometer, like the kind that's used in chemistry, a lot of times they'll even have like a plus-minus value showing the error and what's an accepted error for that thermometer. In our case, we're going to calculate the percent error. So 99.1 is our experimental value, and we're going to subtract the known or actual value for the boiling water of 100 from that. That gives us 0.9. We take 0.9 and divide it by the accepted value of 100 for water, and we get 0.009. We then multiply that by 100, and we're back to 0.9 again. So it's 0.9%. In chemistry, when we're taking measurements, something else we have to take into consideration are what are called significant figures. A significant figure is a measurement that includes all of the digits that are known plus a last digit that's estimated. So say, for example, I have a digital scale and I put an object on it, and this digital scale reads to the first decimal place only. So this object says that it weighs 13.2 grams. Now my scale, that last 0.2 grams, because it only goes to one decimal place, that's not a certain amount. It's an estimated amount. And it could be plus or minus 0.1 gram. So what I actually measured could be 13.2 grams, what the scale read, or it could be 13.1 gram, so minus 0.1 gram, or it could be 13.3 grams. Alright? It could be any of those values. That last digit is said to be uncertain. Now,